Thank you very much for this kind invitation. Especially congratulations to Professor Kasai for the foundation of this remarkable interdisciplinary center in Bratislava. The topic of my talk is future through resilient systems, dynamics, and AI. And that topic goes back to book publications since decades, I must say, since the early 90s with the book on complexity research and artificial intelligence, limits of artificial intelligence, quantum computing, and recently about neuromorphic computing. That means brain-oriented computing, and I will come back to that later on. Now, on that background, I will start with some remarks on complex systems dynamics, and then we will consider concrete examples of application, such as Earth dynamics and civil dynamics, and then the digital tools to handle Earth and civil dynamics. Finally, digital computing up to sustainable AI, and I will end with a roadmap for a resilient Earth and civil dynamics. Let's start with complex systems dynamics. And here I like to begin with an old myth, European myth in Greek mythology, namely the goddess Gaia. Gaia, the great Mother Earth, who sustains all kind of life in an eternal cycle of birth and death. And according to the so-called Gaia hypothesis of the chemist, biochemist, and physician James Lovelock, the Earth, with its biosphere, is a whole organism adapting to changes by feedback mechanisms, following the laws of complex systems. And what are complex systems? They are everywhere. Consider the evolution of complex atomic molecular systems, then cellular and organic systems, the human organism, and finally ecological systems. And from a physical point of view, all these kind of systems are open systems. That means they are in interchange with energy, with matter, or with information, with its environment. And at critical input values of this interchange, these systems generate new patterns and new structures. And on the micro level, we find interacting elements. In a very simple case, here in the first picture, you see only two elements. One element has an effect to another one, indicated by this arrow. And that is a very simple interaction, and it can be described by linear equations, and we can solve these equations since our time as on school. And in the more complex situation, that means even if only one element is more than two, then we find these complex reactions and interaction with all these feedback loops, which are illustrated in the second picture. And in that generation, on the one side, the new structures and patterns can be generated, as I mentioned before, but the whole system can also be destabilized and generate chaos. And that should be prevented in any case. And that means we aim at resilient systems. What means resilient? Now, it means a system which is able to recover itself after perturbation. For example, an organism suffering from a disease, and if you or me are healthy, then we are able to recover ourselves in some time. And that is illustrated here in general for dynamical system by this diagram of an energetic potential landscape with this energy curve. And the state of the system is illustrated here by a ball. And in an equilibrium state, if the system is in balance, then the ball is at the deepest point of the valley. But if the system is perturbated, then the ball starts to roll up and down the walls of the valley. But after some time, it recovers and returns to the deepest point in an equilibrium state. Now, in this case, we call the system resilient because it can recover itself. But sometimes the perturbation is so strong that here in the picture, the ball jumps out of the valley and then it has no chance to recover. And that means a system which is not resilient, and that can all be mathematized. But instead of that, let us consider some concrete examples. For example, the Earth system. The system of our Earth is perhaps one of the most complex systems we can imagine. Here in the state when there were no human civilization, we only had to consider the natural factors which are interacting, such as climate, energy, water. But then with the emergence of human mankind, the civil dynamics came in with several factors, such as population growth of mankind, growth of our industry, social problems, and so on. So it generates this kind of complex feedback loops. And as we already know, these systems are very sensible to local perturbations, which can lead to destabilization of the whole system. And that is especially true in the case of the climate model. The climate model is also highly complex. Many factors are interacting, and at some critical points of values of control parameters, then the system can be destabilized. And after these red lines, we call it sometimes the red lines, the whole system can become uncontrollable. And that is the dangerous situation we are now with our climate on this Earth. And we also can consider an urban system, a complex urban system, a metropolis. Here in the picture, you see the skyline of Shanghai, one of the biggest cities in the world, and depending on many civil factors. And again, if in this complex network there is a local perturbation, that may be, for example, a cyber attack, that may be a disaster of any kind, then it can initiate global cascades of nonlinear effects, which are illustrated here by these feedback loops in these arrows illustrated. So what we need in the end is a policy of early warning systems and a crisis management. And that is also true in economy, in the markets. Here on the in the right picture, you see a time series with the changing volatility of the stock markets, with the turbulent changes of prices month per month. So it is not only a metaphor to say that there is turbulence in the market, because the mathematics, the time series, is very similar to the changing velocity of wind here on the left with a turbulent stream. Now, in general, how should we manage the nonlinear dynamics in a complex social world? And in these pictures, we highlight some of these crucial situations nowadays in the world with the local and global effect. For example, here on the left, a burning jungle along the Amazon River in Brazil, a local effect which can have a deep impact on the global climate dynamics, or here on the right, our sometimes old-fashioned industry with coal and pollution, which can influence our global climate dynamics, or the local dense traffic with its effect to the dynamics of climate, or our water system on Earth. In some parts of the Earth, there is too much water. For example, here in this picture on the left, on the bottom here, that was 2 years ago in Germany, a flood disaster, too much water. But on the other side, the deserts anywhere in the world. So how should we manage these different applications? All these domains are characterized with big, much data. And so that is an application field for AI, for artificial intelligence tools. And in the end, we want to deliver these tools to achieve resilience, as I explained it before. Now, what means AI, artificial intelligence nowadays? Nowadays, AI means machine learning. And machine learning is inspired by another complex system, namely our brain. Our brain is highly complex because millions of neurons are interacting here. And in simplified models of machine learning, there are the neural networks which are illustrated here in these simplified models with these nodes which represent the neurons in the brain, and the arrows represent synaptic interactions. They are weighted by numbers in order to indicate neurochemical intensity of interaction. And then it is said that such a node or a neuron fires, metaphorically speaking, with respect to the brain, or it is excited, or it generates a bit, if the sum of the neighbored inputs here, the neighbored inputs of the neighbored cells is larger than a certain threshold value. And by that, we get a sequence of signals, a data stream, which is led through the architecture of the neural network, which is distinguished into different layers here. By the way, such as the neocortex of the human brain. And these data streams are triggered by different kinds of learning algorithms. One example is supervised learning. Supervised learning means that the system is able to be trained by a certain pattern. A pattern may be the distribution of pixels in a photo. That can be done by adjusting the weights, which I mentioned before, in the neural network according to the different pixels. And then this pre-trained pattern can be recognized by the system among a huge number of other distributions of pixels in photos. That means concretely the system is able to recognize a pre-trained photo among a huge number of other photos. Reinforcement learning means that the system is able to improve its own solutions by rewards from outside. That's a situation of a child in a classroom which is corrected by a teacher. And deep learning only relates to the depth of the neural network. That means to the number of layers. By the way, in the human neocortex of the brain, there are 6. Here in this technical examples, there are only 4 layers. But the dynamics is quite simple and quite similar. Namely, on the first layer, only colored pixels are distinguished. On the second layer, they are connected as edges and corners. Then on the third layer, recognized as partial faces, and then as a whole faces. In principle, that is all. Pattern recognition in a huge mess of data by learning algorithm. That is modern machine learning. But actually, nowadays, the practical use neural networks are much more complex than these simple examples before. For example, in car industry, neural networks consist of millions of neurons, of billions of synaptic weights, and not only 6 layers, such as in the neocortex of the human brain, but hundreds and thousands of layers. Now, anyway, in all these cases, the system this complex system is mathematically represented by a so-called network function, depending on a certain pattern X for training the system. And theta means the distribution of all these billions of weights, which I mentioned before. And in all these applications, in industry, in economy, in medicine, elsewhere, it is the same situation. Namely, these network functions, that means the neural network, should be trained to approximate a certain target. And the target represents a pattern which should be recognized. Here is f, the target function, and here's a neural network. Now theta is trained, the weights to theta star. It should approximate this target function. And now there is a remarkable universal approximation theorem, which can be mathematically proved rigorously. And it says that in any case, if at least the target function here is continuous, it is possible to approximate this pattern. And that means in any case, it is guaranteed that there is a neural network to recognize this pattern. But as sometimes in mathematics, it is only an existence theorem. That means it guarantees that there is such a network, but it says nothing about the parameters of appropriate networks in the special cases. That depends on the cleverness of the creativity of our engineers. Now, anyway, a very prominent example of these very, very complex neural networks nowadays, which everyone knows, are the chatbots. The chatbots which are used in everyday life, I think nearly by everyone. ChatGPT in the United States or DeepSeek in China. And it is amazing what what kind of human abilities can be simulated by these systems. But if we have a look in the machine room of these networks, then we find the situation which I described before. Big data, that means here large language models, and on the other side, learning algorithms, which I mentioned before. Supervised learning, the system must be trained at first by a huge amount of data, and then reinforcement learning. And you all know reinforcement learning if you have ever used or interact with ChatGPT, for example. If you are not satisfied by your answer of ChatGPT, then you know it is able to improve the answer by your rewards. And that means reinforcement learning. That's exactly this algorithm. Now, we are not alone with our chatbots in the world, but we all are embedded in a huge network, which exists since the 90s. I mean, the internet. The internet is a global network of computers in order to support human communication. But nowadays, all the objects, the things, are also equipped with sensors. For example, our smartphone with sensors in order to communicate with it. Or nowadays, the modern cars, you are communicating with your car, or robots, or the aircrafts. We are not aware of that, but the aircrafts are also communicating with one another. And then the modern houses, skyscrapers, for example, which are equipped with digital infrastructure by sensors. And they are able, for example, to regulate more or less automatically the requests of lighting or of heating in these houses. And that is called nowadays the Internet of Things. Not only Internet of humans which are communicating, but the objects, the things by these mentioned sensors. And there are prominent examples of urban systems. And of course, we want to have urban systems which are digital equipment of resilience. That means they must be able to recover itself after perturbation. On the left, that is an elder example from Europe in Amsterdam. Different domains here: civil service, mobility, energy, and health system are integrated by smart technology. And on a very high level, nowadays in model cities such as Shenzhen in China, a kind of self-organizing complex system with intelligent technologies and efficient infrastructures. Or very, very necessary and urgent nowadays, our health system. It is not sufficient to have high tech in the surgery. We must have digital infrastructure of communication. I remember very well the last pandemics when some countries such as Germany or Austria and so on, Italy, had high tech in the surgery, but not in the communication. That was in an old-fashioned way, and there sometimes the communication collapsed. So what we need is digital infrastructure for communication between the patients, the physicians, the medical carer, the service provider. And then I think for the future, one of the most urgent requests, that is the request for circular economy with a resilient computer-supported complex system. What does that mean? In the past, and even in many parts of our Earth, there is still linear economy. And you remember I mentioned linear equations in the beginning. That means here, very simple, you start since centuries with raw materials, then by the raw materials you generate products, and the products are then used, and then we had the residual waste and pollution. But what we need, and that is the first step, is at least recycling of the waste and the pollution. But in the end, we aim here at the situation of a circular economy with sustainable production and sustainable use. That means the residuals must be incorporated again. And to do that, that needs to handle a lot of data that can only be done by digital AI-supported tools. So anyway, what will be the future? The future will be that all these different digital infrastructure will grow together. Here on the left and right of the picture, you see the already mentioned and existing digital infrastructure. And here in a metaphorical way, it is shown the future. Namely, all these infrastructures are growing together, such as these a brain here, which is spreading all over the planet Earth. And here are the examples which are already mentioned, smart city with these digital infrastructure, or smart ecologies. That means AI tools to supervise the great large ecological systems in agriculture, for example, or smart grids for optimizing energetic networks, or the industrial internet. That means more or less automated steps of production, or the circular economy and health systems, which I mentioned already before. And in the end, I think we should aim at a resilient political system. That means with political balance, after perturbations, digital conflict management, communication. But you know, that is until now only a vision we should try to realize. But all that seems to be nice, but actually it depends on another big problem and challenge of our mankind and planet. That is our energy problem, because digitalization means a lot of energy, and that is illustrated here. All our AI applications nowadays depend on our classical digital computers. The first one was constructed in the 40s of the last century by John von Neumann in the US. And therefore, the architecture of these kind of digital computers is called von Neumann architecture. And that means that there is a strict separation between a processor of digits and a memory of digits. And all the increasing mass of data must be elaborated by these two units. In the end, the increasing mass of data nowadays must be pressed through this architecture. And sometimes it is called the von Neumann bottleneck. It is like the ketchup in a ketchup bottle, when the ketchup should be pressed through a small bottle neck. That is a situation which needs a lot of energy. So in the near future, a large part of the energy consumption on Earth will be needed in digitalization, and quite different to that evolution. Quite different to that nature, especially our brain. Our brain only needs 20 watt. It is amazing for all the abilities of the human brain. 20 watt, that is a small energy of a small lamp. How is it possible? Mainly by the completely different architecture. No longer the strict separation here on the left between memory and processor, but a neural network. A neural network such as in the brain, with these neurons here and the arrows indicating the living synapses. And such a living synapse in the brain is able to integrate both abilities, namely the processor and the memory. And there is not only one synapse in the brain, as you know, but there are billions of them. So in the brain, in the living brain, there is no danger of a von Neumann bottleneck. But we still use neural networks only as simulations on these classical digital computers. And so there is no advantage of energy consumption. So the question arises, is it possible to realize such a neural network in hardware? Perhaps not in wetware with living tissues like in the human brain, but at least in hardware. And the answer is yes, we can. It started with first theoretical predictions in the 70s of the last century. Then there were theoretical suggestions of a kind of transistor which is able to integrate processor and memory, such as a living synapse. I was involved in mathematical modeling since 2000, and the idea was to construct an electrical network with electrical units and electrical connections, grids, in order to simulate the neurobiological interactions of the living neurons and synapses. And these kind of transistors, which I mentioned before, by the way, they are called memristor. Memristor is a word which combines memory and resistance. And these memristors should, in these models, simulate the living synapses. And that is illustrated here in the left picture. There is a layer with a grid, and here, instead of the living synapses, you have these memristors here, and from the left, voltage comes in, and then it is computed in an energy-efficient, fully parallel, analog in-memory computation by vector matrix products. Anyway, it is able to generate the output, namely current. And that is highly energetically sufficient, more sufficient than the classical approaches, very similar to the human brain, and therefore it is called neuromorphic computing. Now I'm involved in a research project in Germany. I'm in an advisory board, and they are not only modeling that, they try to realize it with the industry. That means to build chips, these very efficient chips, and it needs, by the way, no rare materials. It needs very basic materials such as titanium dioxide, which you sometimes find in your sun cream. Anyway, that is a nice approach to consider the close connection of, on the one kind, digitalization, but on the other kind, our energy problem. And in these research groups, new ideas recently came up, namely to apply, instead of electrons in an electrical circuit, to apply photons. Photons, that is amazing, with optical electrical units as neurons mimicking the neurons. That is absolutely amazing if it will be realized in the future, at least because with photons you are calculating in a nanosecond scaling and no longer millisecond scaling, such as electrons in electrical circuits. And concerning the energy consumption with photons, you come very close to the brain, namely 75 watt. And you remember I mentioned for the brain 25 watt. But to be honest, that is still in its infancy. Also, it's a nice perspective, which I like, is to combine this photonic approach with quantum computing, because photons are quantum systems, and then you would have all these amazing advantages of quantum computing, with this immense increase of computational power. And anyway, to make a long story short here in this lecture, these kind of neuromorphic computing aim at the reduction of energy consumption, and with that on a sustainable AI. That means AI not with any relation and with any consideration of our energy problems, but in a sustainable way. Now, let me end with a roadmap for a resilient Earth system. This arrow should illustrate this roadmap. At first, we all, in all the different countries in the world, have at first to do our homework. And our homework is decarbonization. That means renewable energy, but that will be not sufficient. We also need nuclear energy and alternative fuels. And with that, in the next step, we should realize the sustainable development with energy efficiency, increasing flexibility, circular economy. And then we need, of course, digitalization, digital tools to realize that with the Internet of Things, with artificial intelligence, which I explained before. And in the end, we aim at resilient systems. That means the sustainable development goals, which are requested by the United Nations since many years, must be integrated into our technologies of complex infrastructures. But that should not be my last slide. You remember I opened my talk with the remembrance of an old myth, European myth, the goddess Gaia. And let me end now with Eastern wisdom, and that is the bamboo. Like bamboo in the wind, adapt and shape the dynamics of a resilient world in balance. I thank you for your attention.